Hello, welcome to the 35th class in our course the physics of materials. In the last class we looked at how bands come about and how band gaps come about from the approach taken by two different ways of approaching this problem. One was the free electron approximation and the other was the tight binding approximation. So we have actually looked at the free electron approximation in considerable detail. We briefly looked at the tight binding approximation, and I told you the reasons why we focus more on the free electron approximation, because that is more relevant for metallic systems and such. But in principle both of them should give us the same kinds of results. They should predict the same, make the same predictions, and largely they do. It is just that the tight binding approximation is more suitable for insulators and semiconductors and such. So and the free electron approximation is more suitable for metallic systems, more appropriate at least. In the context of both these approaches we have seen where bands arise from, and in particular the fact that Brillouin zones interact with the Fermi surface and tell us the bands and band gaps that exist in a material in the free electron approximation, and the importance of interatomic spacing when it comes to tight binding approximation. In this context, in both approaches we see that in principle they have the details in place to tell us why anisotropy should exist in a material. Certainly in the case of free electron approximation, the geometry of this crystal structure is reflected in the geometry of the Brillouin zone, and therefore that is directly reflected in the manner in which the Brillouin zone now interacts with the Fermi surface. Okay, so and therefore the locations where there is an interaction, the extent to which an interaction exists, all of these are directly related to the shape of the Brillouin zone and where it is with respect to the Fermi surface, and therefore the directionality arises as a direct result of this interaction. So in this context we have seen the importance of the Fermi surface. We also briefly saw that once you understand that there are bands and band gaps, you can actually even manipulate materials and increase or decrease the band gap and therefore change their properties. Also in the context that we know that there are bands and band gaps, we briefly saw how metallic systems differ from semiconducting systems and differ from insulating systems with respect to those band gaps and bands. In this class we will spend more time on the semiconducting systems, semiconductors in general. We will see where many of the concepts we have learned so far are how they are relevant to the semiconductors, for example the Fermi surface, and we will also see the importance of the E versus K diagram and what it tells us about properties. More specifically we will see why the E versus K diagram gives us much more useful detail of the system than a flat band diagram, which in fact in some sense captures the same, it still tells us what is an allowed energy level and what is a band gap. So the E versus K relationship is important and we will see why it is important, and also in the context of the semiconductors we will also get an idea of the optical properties and how all of this information comes together when we talk of optical properties of materials. Okay, so this is what we will do. So when we look at semiconductors, in principle we have they are classified as intrinsic semiconductors, and extrinsic semiconductors. In principle the main difference really is that in intrinsic semiconductors the property that you see is that of as pure a material as you can get, and there are no deliberate additives to this material. You are seeing the property of that material, and in extrinsic semiconductors we have deliberately added some dopants which change the manner in which the material responds. But in a more fundamental sense what we are saying is that intrinsic semiconductors are those where the properties we are measuring, at least in this case the say the carrier concentration and such, is a direct result of the temperature of the material. It's primarily dependent on the temperature of the material. That is what decides the carrier concentration in an intrinsic semiconductor. In an extrinsic semiconductor that is not necessarily so. In fact there are regions of temperature where the behavior of the semiconductor is dictated by factors that are completely unrelated to temperature. They depend entirely on the extent of doping that you have done to it, okay, or the extent of additional elements that you have added to it. So in intrinsic semiconductors, so we will first look at intrinsic semiconductors, then we will talk about extrinsic semiconductors. So of course the standard classic examples is basically the intrinsic semiconductors can be elemental or compound based. So these are elemental semiconductors that are intrinsic, they are group 4a elements, silicon and germanium, and we could also have compound semiconductors that are still intrinsic, and they would consist of elements which are on either side of this group 4a. So we could take a 3a element and mix it with a 5a element, and then you would get a compound semiconductor. You could also take a group 2b element and mix it with a 6a element, and you would get a compound semiconductor. So that is basically what you are looking at. So we can have 3a and 5a elements. So these are called 3,5 compounds. Right, so these are called 3,5 compounds, and so an example would be we could have gallium arsenide, we could also have indium antimonide. These are compound semiconductors, but they are intrinsic in nature, so they behave as though their behavior response is really based on temperature. You could also have 2,6 compounds, so 2b and 6a compounds. So an example of that would be say cadmium sulfide. Okay, so this would then be called a 2,6 compound for obvious reasons. Okay, so this is a 2,6 compound. You can go further and further in the periodic table on either side of group 4a, but the problem then arises is as you go further and further away, the electronegativities and electron affinities of theirs begins to change so much that you are favoring more an ionic bond rather than a covalent bond, and these are elements that this kind of a behavior you see mostly in situations where you have a covalent bond rather than an ionic bond. In an ionic bond the electron simply gets localized, so it is not in a position to be shared or moved around, whereas here they move around. So this is it gets trapped, and so this is not what we are looking at. We are looking at covalently bonded elements. So the further away you go, it becomes more and more ionic. So that is the issue that you face. Okay, so this is a compound. These are compound semiconductors 3, 5 and 2, 4. We could look at these elements depending on where you encounter them. You will either hear the description in terms of bonds and how the electrons are shared between bonds, or alternately we look in terms of the band structure. Okay, so in our discussion we prefer to use the band structure. Ultimately we are talking of the same thing, so therefore only whatever is convenient to us is all that we use. Okay, so we are going to talk in terms of band structure. So this is what we have. If you are talking of extrinsic semiconductors, then we could take silicon, okay, and so we can dope it with say gallium, okay, or if you say you dope it with arsenic for example, then you will have additional electrons. So this would, so any basically a group, this is group 4a. So if you dope it with any element that is from the group 5a, then basically you have an n type semiconductor, because you have additional electrons from the arsenic which can roam around, or you could dope it with so for again silicon with say gallium, which is 3a, then you would have a p type semiconductor. Which means you are short on electrons, and so and that is why it is called p type. In principle ultimately there are some charge carriers in these materials, and The two charge carriers that we define are that the first one we are very familiar with, it is the electron. So electrons are charge carriers, and so that is our discussion when we talk of intrinsic semiconductors and so on, this is what we are starting out with. But every time an electron, if you have an electron that is sort of conspicuous by its absence, so to speak, so then if an electron is absent from a location, then we treat it as though an entity with opposite charge exists at that location, okay. So that would be a hole. So it has the opposite charge of an electron, so that is what we have electrons and holes. So in terms of when you talk of bands, so when you talk of a filled valence band and an empty conduction band, every time you take an electron from here and move it across here, okay. So now you have an electron here, you have left behind a vacant location here, okay. You are leaving behind a vacant location here sort of, so that is treated as a hole. So for every electron that is going into the conduction band, it leaves behind a hole in the valence band, okay. So that is how we look at this system, alright. So we have electrons and holes which could participate in the conduction process, both of them contribute in some ways to the conduction process, and so therefore they are important charge carriers. If you have a system where you have dominantly a large number of electrons relative to holes, that would be an n-type semiconductor, and another case where you have a significant amount of holes relative to the number of electrons that can move around, then that would be a p-type semiconductor, and those are accomplished by doing appropriate doping to a material in group 4a, okay. So this is what we are looking at, fine. So this is what we are looking at in terms of the possibilities of an electron being present at some location and a hole being present at some other location. So now in terms of conductivity, right, we originally wrote the flux of current or the current density, so J is simply E times the conductivity sigma E, right. So this flux of current is also the number density of the charge carriers times the charge that is being carried times the velocity with which they are moving. So let us say that is the drift velocity, so NEVD. So this is also equal to NEVD, or rearranging this, if you just take this second part of the equation here, this equation here, so sigma equals NEVD by the field. So this is the field, this is the conductivity, this is the number density of the charge carriers, this is the charge on the charge carrier, and this is the drift velocity of the charge carrier. So if you look at this term here is the mobility of the charge carrier. We define this as the mobility. It is the velocity attained by the charge carrier per unit driving force, driving field that exists there. So therefore this is simply N E, and mu E is the symbol used for the mobility of the charge carrier. So that is what we have here, okay. So this is what we have. As I mentioned in an intrinsic semiconductor, for every electron, if you look at intrinsic semiconductors, for every electron in the conduction band, there is a hole in the valence band. Okay, so there is a hole in the valence band for every electron in the conduction band, because there is as it moves away, it leaves behind a hole. Now when you apply a field, the electrons in the conduction band can move, and effectively the holes in the valence band can also move, except they will move in the opposite direction. In principle, you can actually step back and say, in fact it is only the electrons that are moving, but as the electrons fill up that whole location, you can think of the hole moving in the opposite direction. Okay, so in principle the charge, it's easier to describe it in terms of electrons and holes, so we talk in terms of electrons in the conduction band and holes in the valence band. Okay, so both of them can participate in the conduction. So in fact for a semiconductor, the conductivity that we get is N times E times mu e plus, if n is the number of electrons per unit volume, we can designate the number of holes per unit volume using p times the charge, again its charge is simply the charge of the electron, it is just an opposite charge, times the mobility of the hole, okay, mobility of the hole. So we have n e mu e plus p e mu h, that is the conductivity of a semiconductor, okay, so at a given temperature. So that is what we are looking at. Now in an intrinsic semiconductor, for every electron in the conduction band there is a hole in the valence band, therefore n is equal to p, whatever is the number density of free electrons, the charge carriers, we will not call it free electrons, the number density of electrons per unit volume in the conduction band, the number of electron holes per unit volume in the valence band is going to be the same, p, right. So n is equal to p, and that is called the intrinsic charge carrier concentration or intrinsic carrier concentration, okay. So n is equal to p is equal to ni, or the intrinsic carrier concentration, and okay, so that is for an intrinsic semiconductor. So therefore sigma is simply ni times E times n mu E plus mu H, okay. So ni times E times mu E plus mu H, this mu E and mu H are not actually the same, even though you are saying, you know, I mean electron moving in the in this case we are talking of electrons moving in the conduction band, and that case we are talking of holes moving in the valence band, okay. But the mobility of the electron is different from the mobility of the hole. In general electron mobility in these situations is higher than that of the hole mobility, and in a sense we can rationalize it by thinking that, you know, if you are going to have electrons moving in relatively in a situation where most of the states are empty, which is the case of the electrons which are now running across in the conduction band, they are more likely to move around more freely, right. So it is a direct reflection of the environment in which they are moving, whereas the electrons which are sitting in the valence band, where they are largely filled except for the few electrons that have few electron states which have become vacant, in other words for the few holes that are there, those electrons are actually moving with much more sluggishly, because they are faced in a, they are sort of moving in a crowded area. So therefore the holes, which is effectively the other way in which we are looking at the electron movement in the valence band, their mobility is less. That is the way, that is one way in which we could rationalize the situation. But anyway, the point is that the electron mobility and the hole mobility are not necessarily the same, and therefore we write Ni, the intrinsic charge carrier concentration, times the charge times the mobilities of those two species, okay. So this is what we have. Now in this context I also want to point out that when we wrote the intrinsic semiconductors, in terms of what we have already discussed, I pointed this out towards the end of last class. For so this is the valence band, and that is the conduction band. In terms of what we have discussed, the important parameter that we have of relevance is the Fermi energy, and so for an intrinsic semiconductor the Fermi energy is in fact defined as being the midpoint of this band gap. So this is where you have the EF, okay. So this is how you write it for a intrinsic semiconductor. Now the situation is slightly different for an extrinsic semiconductor. Extrinsic semiconductor, okay, we could have an N type or a P type. So let us start with an N type. In an N type we have again a conduction band and a valence band, and say for example we have introduced a group 5a element into this group 4 element. So what will happen is you have additional electrons, those electron levels are actually very close to the conduction band. okay. So they can very easily get into the conduction band. In fact, that is the reason why they dominate the behavior of an n type semiconductor, alright. So so this is the impurity level, okay, and therefore for in terms of the highest energy level now being occupied by the electrons and so on, this is what defines it much more than what is sitting here. So therefore for an extrinsic semiconductor, n type extrinsic semiconductor, this is now the Fermi energy. Fermi energy moves to a value very close to the conduction band, the bottom of the conduction band, okay. So that is what happens for an extrinsic semiconductor of n type. If you go to p type, so let us just do p type here, an analogous situation but with opposite effect is what we are going to see. So p type would look something like this. We have the conduction band, we have a valence band, this is full. Now the impurity you are introducing is a group 3a type of element, let us say that is what we have done, and therefore that has less electrons than what the group 4a is in a position to provide. So in terms of bonds and such, it has one less electron. In terms of a band structure, it means that in terms of energy levels, it has an acceptor level, which I will indicate as circles here. It has an acceptor level very close to the top of the valence band of the parent material, okay. So what happens is, the moment you raise temperature, the electrons do not have to go all the way up to the conduction band to conduct, they simply have to get into this acceptor levels here and they can start conducting, okay. And therefore the so this now defines the position of where the highest energy electrons are, so to speak, or in that sense if you want to describe it, and so this now defines the Fermi energy for a p type semiconductor. So the Fermi energy of a p type semiconductor is virtually at the acceptor levels of a p type semiconductor, which is very close to the top of the valence band of the p type semiconductor. The Fermi energy for a n type semiconductor is effectively at the donor level. So this is the impurity level, donor level, and this is the acceptor level. So for a n type semiconductor, the Fermi energy is at the acceptor level, or virtually at the acceptor level, I am sorry, virtually at the donor level of the n type semiconductor, okay. So Fermi energy is virtually at the donor level for the n type semiconductor. So so this is important to understand this picture because when you look at what is happening when you make semiconductor devices, when you take an n type semiconductor and put it in contact, direct physical contact with the p type semiconductor, I mentioned that the Fermi energy is like the chemical potential of the electrons. So if the chemical potential of the electrons is high on one side and low on the other side, they will flow, it will flow till the chemical potentials become equal, okay. So that is how when you put different types of semiconductors together, electrons move between them to ensure that the Fermi levels attempt to equalize, okay. So that is how this process occurs, okay. So now we have spoken often about the conductivity of the materials, and we have seen now that for most materials, I mean we are looking at the charge carrier concentration is a very important factor that contributes to the conduction process, right. So it is of interest to see how the charge carrier concentration varies for an intrinsic semiconductor versus an extrinsic semiconductor as a function of let us say the temperatures at which you are subjecting the material to. So what you will actually see is something like this. So this is in a linear scale, so let us say this is about 200 Kelvin, this is 0, this is okay, so this is 0, this is 100, this is 200, this is 300, this is 400, this is 500 Kelvin, and this is also 0, this is put it here 10 power 21 per meter cube, 2 into 10 power 21 per meter cube, charge carrier concentration and so on. What happens is if you look at the extrinsic semiconductor at very low temperatures, I will just draw the behavior and I will explain it to you. You see a behavior with respect to temperature that looks like this, okay, of charge carrier concentration for an extrinsic semiconductor. For an intrinsic semiconductor you see a behavior that looks like this. Okay, so intrinsic semiconductor you see a behavior that looks like this. The point is this, for an extrinsic semiconductor what happens is, as you initially there is a region at very low temperatures which is called a freeze out zone, where the energy is simply too low for any electronic transitions to occur, and so therefore the electrons remain frozen, they do not get into the conduction band nor do they get into the acceptor levels, nothing happens, everything looks frozen. Then at once you cross a certain threshold, that is enough energy for the extrinsic the dopant levels to participate in the process, because they require only a very small amount of energy to either take electrons from the conduction band into the acceptor levels which are very close to the conduction band, or to take electrons from the donor levels and put them into the conduction band which is very close to the because it is very close to the conduction band. So you need only a tiny amount of energy to do that, as opposed to taking an electron from the conduction band from the valence band all the way to the conduction band, right. If you wish you can look here, you will require a very small amount of energy to move this electron up here or to move an electron into this acceptor level. Relatively speaking, you need a larger amount of energy to move an electron from here all the way up to here. So that is the difference, okay. So this is a larger amount of energy, this is energy in the axis, so this is a larger amount of energy, this is a small amount of energy, this is a small amount of energy. So at very small temperatures you have enough energy to do this or to do this, and so and you essentially saturate the process, everything that can go goes off as soon as you cross some temperature threshold, almost everything that can go here goes off there immediately, and that is a finite amount of levels here as acceptor levels or donor levels, because that depends on what doping you have done to the system, what percentage doping you have done to the system, right. So that is finite. So immediately the conduction process starts, you have a fair number of charge carriers, but that stays constant for a long period of time. Because that is a finite process relatively speaking, because there is a very not just finite, it is a very small number of dopants, that small amount of dopant that you have put. Here on the other hand you will take a lot of energy before you start moving electrons across, but once you cross a certain threshold you can keep on, as you raise the temperature you can keep on increasing the number of electrons that get into the conduction band, okay. So you can keep increasing the charge carrier concentration by raising the temperature. So that is what you see here. For the extrinsic semiconductor, initially everything is frozen, there is not enough energy to move the electrons across even the small distance that they have to move in energy, small amount of energy. Once you cross a certain threshold, all the acceptor levels participate or all the donor levels participate, so you saturate out. So this now becomes representative of the dopant concentration, because the dopant concentration will impact the charge carrier concentration directly, and so this becomes based on your dopant concentration, this can move up or down, but it stays constant. As you raise the temperature you have already saturated it out, there is nothing more to put into the dopant level or from the dopant level, so it stays constant. As you go to very high temperatures relatively speaking, then intrinsic transitions also begin to occur, okay. Even in an extrinsic semiconductor, nothing prevents a transition from the valence band to the conduction band, you simply have to have enough energy to enable the transition. So if you get to high enough temperature the transition will occur, so therefore you can start seeing the charge carrier concentration once again increase, and that will of course, if you look at an intrinsic semiconductor there is nothing happening till you come to that temperature, high enough temperature, so that you provide enough energy for that transition from the valence band to the conduction band. From then on as you raise the temperature this keeps going up, okay. So because you are putting more and more electrons into the conduction band. So in terms of an extrinsic semiconductor, this is called the freeze out zone. Up to this temperature it behaves like an extrinsic semiconductor. Extrinsic zone or extrinsic conduction or extrinsic behavior, okay. So extrinsic behavior you have here, and then once you cross this temperature range here you start seeing intrinsic behavior. Right. So you can get extrinsic behavior here and then intrinsic behavior here. So as you raise the temperature eventually it starts behaving like an intrinsic semiconductor, the material begins to behave like an intrinsic. So this is what you see. The other parameter we wish to know, so this is how the charge carrier concentration. So when we look at the fact that conductivity is a function of the charge carrier concentration, the charge of the electron and the mobility of that carrier, right. So you have conductivity sigma is n, charge carrier concentration, charge of that charge carrier times the mobility of the charge carrier, mu e or mu h or whatever you want to do. So these are three parameters. We have already seen how n can vary for an intrinsic semiconductor or an extrinsic semiconductor. E is fixed. It is of interest to see how the mobility of the electron will change. So mobility of the electron, if you wish to see, what you will see, mobility of electron or mobility of hole, we can look at it as a function of temperature or as a function of impurity concentration. So if you see in general what you will see is let us say this is in a log scale, this is -3, -2, -1 log of mu, okay, and this is the impurity concentration 10 power 15, 10 power 16, 10 power 17, 10 power 18, we just put something down, 10 power 19, 10 power 20. So this is the impurity concentration per meter cube, okay, so per meter cube. So or this is atoms per meter cube if you want to call it. What you will see is that in general you will see a trend that looks like this. As you raise the impurity concentration, the mobilities decrease. So this is something like, this is mu e, this is mu h. I told you that mu h generally tends to be lower than mu e. So the mobility of the carriers begins to decrease. So in terms of our understanding, so these are all the things that are occurring. This is how the charge carrier concentration is going up or changing with temperature. This is how the mobility is changing with impurity concentration, and similarly even with respect to temperature. If you put up mobility values as a function of temperature, so again we will say same kind of temperature range 0, 100, 200, 300, 400 and 500. These are in Kelvin, okay, so this is Kelvin, this is also Kelvin. And if you look at the mobility values, similarly we can write -3, -2, -1 and 0. So that is what we can look at. So if you see what you will see is we have to now define this is as a function of temperature, mobility as a function of temperature, which we can define at specific impurity concentration values. So for a given impurity concentration value, so the general trend will look like this. We are only drawing schematics here. You are looking at some behavior that looks like that. With temperature it is going down or something like that is the, and this is impurity concentration, okay, increasing. So whatever, if you want to look at these values here, let me just say this is 10 power 20 per meter cube and so on, 10 power 19, or this is at higher concentration. So this is 10 power 20, 10 power 22, 10 power 25 per meter cube. So as you so basically as you increase the impurity concentration, the mobility is coming down. As you raise the temperature, mobility is coming down, okay. So so these are all the parameters that affect the conductivity, okay, in terms of this equation here. And this is just, I will remove this mu so that there is no confusion, it is just a mobility of whatever is your charge carrier, right. So but ultimately conductivity goes up, okay. So we have to understand this fundamental idea that when I mentioned this, that when we looked at metals, if you look at the conductivity of a metal, it has a positive coefficient for the thermal coefficient for resistivity. So as you raise the temperature of the metal, the resistance of the metal goes up or conductivity of the metal comes down. This is not true for semiconductors, it is not true for ionic conductors and so on. and the fact that it is not true for semiconductors should become consistent with this picture that we have here. What we see is as you raise the temperature, actually the mobilities of the species decreases, but what is so therefore this term is going down, mobility of the conducting species is going down, and in that sense it is the same as that of the situation is the same as that experienced in the metallic system. In the metallic system also the conductivity comes down as you raise temperature, because the mobility of the species, the electrons, begins to come down, because it is now having more collisions with whatever are the other scattering, it is encountering more scattering events, right. So therefore in terms of mobility the general trend is not is basically the same whether you are talking of a semiconducting material or you are talking of a metallic conducting material. In general, as you raise the temperature, mobility is going to come down in general, but what changes the pictures dramatically is this value of n, okay. In a metallic conductor we simply talk of the number of free electrons per unit volume. That number of free electrons per unit volume is a fixed number, we are not or largely it is a fixed number, it is not something that we have manipulating in a significant way. It is a large number, but it is a large but largely constant number, we are not really manipulating it in a in any significant manner. Therefore this sort of remains constant, the charge on the charge carrier remains a constant, mobility keeps coming down in a metallic conductor, therefore the conductivity of the material comes down as a function of temperature for a metallic conductor. For a semiconducting material again mobility is coming down as a function of temperature, this E is a constant, but this N actually increases with temperature, right. You have seen here as you go up in temperature the number of charge carriers per unit volume is actually going up, okay. So this is per unit volume per meter cube, okay. So charge carriers per meter cube. So the number of charge carriers per meter cube is going up, it goes up abruptly in the case of an extrinsic semiconductor, it goes up gradually if it is an intrinsic semiconductor, but it goes up. So therefore this N is always going up with temperature. What we generally see is that for the semiconducting systems the manner in which the N goes up more than compensates for the manner in which the mu comes down, the rate at which N goes up more than compensates for the rate at which mu comes down, okay. As a result we see an increase in conductivity. So from all that we have now understood, we now see that there is a fundamental difference between what a metal is and a semiconductor is in terms of its conduction process, and we are able to see it because we are able to find out the parameters that affect the conductivity process. We see that the charge carrier concentration is the way in which the charge carrier concentration is varying as a function of temperature is significantly different for a semiconductor than it is for a metal, and that is the reason why the conductivity behavior is so different. In terms of the mu actually the behavior is more or less the same, okay. I will also point out that for a metallic system the N is actually a very large number, for a semiconductor relatively speaking the N is actually a small number compared to a metallic system. That is the reason why overall the conductivity of a semiconductor is less than the conductivity of a metallic system, okay. So the electronic conductivity of a semiconductor overall average is going to be less than the average metallic average conductivity of typical metallic systems, okay. So the sigma value of a semiconductor is going to be less than a sigma value of a metal, but the behavior of the sigma is going to be different. For a metal as you it will start at a high value, but it will keep coming down as you raise temperature. For a semiconductor it will start at a low value, but as you raise the temperature it will go up, okay. So that is the difference between the two, and this is how we understand it from fundamental principles in terms of how the constituents of the material are behaving, in this case the electrons are behaving, what is happening in terms of transitions, and how they are contributing to this the experimental parameter, the conductivity, which is what we measure. Alright, so we have now had a reasonably good overview of the semiconductor system, and we have seen how important characteristics of the semiconducting system correlate with a lot of things that we have learned, okay. What we will do is also look at the optical properties displayed by different materials in the context of all the band gaps and so on, and then see if what we have learnt helps us get better insight into the optical properties of materials, which we will do right now. So now when you talk of optical properties, we are talking first of all of often we are talking of light in the visible spectrum. So we are looking at wavelengths in the visible spectrum, okay. So what happens is the energy of those wavelengths is E equals h nu is equal to E h c by lambda, okay. Now if the incoming radiation has enough energy, if this h nu is large enough that when it encounters a material with a band gap Eg, okay, so this is Eg, if Eg, okay, if h nu is greater than or equal to Eg, okay, so h is a constant, Planck's constant, so it rather therefore if you keep raising the frequency, at some frequency you will have enough energy in the incoming radiation that it is greater than the band gap of the material that is on which the radiation is incident, then it will enable a transition from here to here, okay, and so at that point the material begins to absorb this radiation, okay, so that is what is happening. Now the important thing is, so any frequency higher than this, any energy higher than this material will absorb, any frequency less than this will actually get transmitted through the material will not be able to interact with that radiation. So if you make a defect free material, physically defect free material, it will of this kind of, with this kind of a band gap, what you will generally see is if you put low enough frequencies, the it will be transparent to those low frequencies, only when you cross a certain frequency it will start absorbing that frequency. By the same token, this is the reason why metallic systems are opaque, because in metallic systems there is virtually no gap, you have either a half filled energy level, so therefore there is virtually no even for tiny amounts of energy there are available states immediately above what is filled, so therefore a metal can keep absorbing energy over a very wide range of frequencies, and that is why essentially when you look at a metal it looks opaque, if light falls on it, it gets absorbed, so that is why it looks opaque, whereas this looks depending on what semiconducting material you have and what band gap it has, it can be transparent, okay, so that is how we see this behavior. But there is one important detail that we would like to add to this picture, which is based on our understanding or the level of detail that we have learnt of these systems and what we have understood and built in our models. We have seen, we drew E versus K relationships, and we basically saw that based on where the Brillouin zone is, we saw a behavior that looks like this. And we said that this is a band and this is another band, okay, and let us assume that this is filled. Okay. Now so in our discussion we simply pointed out that in a flat band structure this would then be the Eg, which is then corresponding to this value here, Eg. Okay, so if you draw it to scale, so that is where it is, so this would be somewhere here then, okay, so that it matches up correctly, so that is the Eg that you are looking at. Now the important thing to note here is that this is a diagram, as I mentioned, when you look at a 3-dimensional structure, the Brillouin zone has a certain shape to it, and therefore exactly where the Fermi surface touches it is going to differ based on the direction in which you look at the Brillouin zone and the Fermi surface, right. So in some places it may touch the Fermi surface, the Brillouin zone very quickly, in some cases it may be little further away from the Brillouin zone, so these possibilities are there. Therefore the location of this and so it is important to understand that the location of the Brillouin zone boundary or rather the Bragg plane in this case is going to differ based on the direction, right. So based on the direction that we look at it, this is going to differ. So we can easily have a situation where I am plotting now one direction in the lattice symmetry along this side and a completely different direction along this. I am just say, let us say this is the 1 1 0 direction, this is the 1 1 1 direction, okay. So these are two different directions in the lattice, just for arbitrary description sake, and we will just say that in one case we see a behavior where the Brillouin zone looks like this, or rather the band structure looks like this, okay. So this is how it looks, and in another direction we have a situation where the band structure looks something like this. okay. So now what do we have here? We have a situation where the location of the Brillouin zones, I am just saying that it is a little further apart here, okay. So so it is further apart here, these are much narrower, because they are much narrower this band ends faster here, it ends at a much lower energy level in this direction, okay. So the band ends in is at a lower energy level in this direction, the next band starts at a correspondingly lower level in this direction, relative to the end and start of bands in this direction, okay. So now supposing the Fermi energy level is here, I will just say this is EF. So we have a situation where the valence band is defined by the band structure in this direction. I just say this is 110 direction, let us say, right, and this is 111 direction, okay. So I will just put it this way. This is just arbitrarily we are just picking two directions just to illustrate the point. Let us just say that in the 111 direction it looks like this, in the 110 direction it looks like this, just a schematic. So now what we are saying is that the band structure is like this in in terms of the flat band depiction, it looks like this on the side where in the 110 direction. In the 111 direction we are actually seeing something else. So the next available band here in the 110 direction is here, whereas the next available band empty location in another direction is actually lower in energy, right. So this is again a filled band here. So if you look at the in both cases maybe the band gap may be the same, but regardless if we just look at this level here, we find that the highest occupied level in the valence band is closer to the lowest unoccupied level in the conduction band in a different direction, okay, in a different location in K space, in a different location in K space. So the band gap, rather than being defined by this, is now defined by this. So with less amount of energy you can take an electron from here and move it to here, because the band structure is different in different directions. This picture clearly shows you that you can have anisotropy. Why there is anisotropy in the material? Because the E versus K relationship is the same, but where the Brillouin zone boundaries appear is different for different directions. So therefore you can get a transition from here to the next available level, which is the closest in terms of energy. In terms of energy it is closest by going to a different direction, but in terms of direction it is a different direction. So that is the thing. So the lowest available energy level is coming up here closer to this highest level here, relative to the band that is showing up there, okay. So so you can have a transition that goes just this much distance and gets into a available empty energy level here that is permitted, and therefore this transition is allowed, okay. So the band gap tends to get defined by this distance rather than by that distance. When you have such a situation where the lowest energy, the highest energy that is occupied in K space and the next available lowest energy in that is vacant in K space, which are there in two different directions, then that is called an indirect band gap material. Or in this case an indirect band gap semiconductor. So this is an example of an indirect band gap semiconductor where an electron, the highest occupied energy level is in one direction in K space or one location in K space, and the lowest unoccupied, the next lowest unoccupied level is at a different location in K space, okay. So these are two different locations, this is in this direction, that is in the other direction, it is completely different direction. So this is how we have this. So such a material is called an indirect band gap material, whereas there are definitely other examples where the lowest occupied, the lowest unoccupied state and the highest occupied state are both in the same direction in K space, okay. So where you do not have this situation, where you simply have only this part of the picture holding true, and that is fine, okay. So in that case you the band gap is still defined by this original material. So that would be a direct band gap semiconductor, okay. So from here to here if you go, that is a direct band gap semiconductor. The way we have drawn it here is an indirect band gap semiconductor. I will just, for clarity's sake, I will just add that here, so that we can see that this is a, so this is a direct band gap semiconductor. Okay. So we see fundamentally therefore that we see that there can be anisotropy, we clearly see how anisotropy can exist, and that these are two different situations. What is the result of it? The result of it is simply this: when you use the material for optical purposes, the material that ultimately you have to provide the amount of energy corresponding to the band gap to enable the transition. However, how easily the transition occurs also depends on where the whether the location of the transition is in exactly the same position, or it has to go to some other location in the lattice side. Okay. So therefore, in general it is found that indirect band gap semiconductors are less efficient in participating in optical processes than direct band gap semiconductors. Okay. So direct band gap semiconductors are much more efficient in handling optical processes than indirect band gap semiconductors. So for example, this is silicon is an indirect band gap semiconductor, gallium arsenide is a direct band gap semiconductor. Gallium arsenide is a direct band gap semiconductor, this is an indirect band gap semiconductor. So when you try to make a laser or things like that, this is the kind of material that is preferred, not this. Okay. So we will wind up our discussion today with basically these comments. We have seen today, we have looked at semiconductors in detail, we have looked at optical properties of materials, and we have looked at both of these from the perspective of all the things that we have learned so far: the Fermi energies, the Brillouin zones, the Bragg planes, and the band structures. And we have recognized now that the E versus K relationship is a very important feature, which gives us much more information about what the material will do than simply the flat band structure. The flat band structure will not tell you whether something is a direct band gap semiconductor or an indirect band gap semiconductor. So simply looking at the flat band structure, we cannot decide whether the material is useful for a particular purpose or not. Knowing the E versus K relationship, you can say so, because that will tell you whether the electron has to go to a different location to undergo the transition, or it can undergo the transition at the same location. If it has to go to a different location, it has to have energy to go up as well as go to the different location. So these are two different processes. Here it simply has to have the energy to go up. So the probability of this occurrence is much higher here than it is here, and that is why this works better for optical purposes. Okay. So with that we will conclude this class. We will take it up in the next class, where we will look at other properties of materials. Thank you.